So we have covered all of the biovalidation topics except for the biocompatibility. Here we took two things that we were concerned and unsure about: a strong adhesive tape and a bioplastic film. And we also took a control for comparison reasons. After 24 hours, we took 4 samples for each one, and by looking at the data, we can see that in the control, in the tape, and in the plastic, there was growth comparing it to the initial concentration. However, we can see that in the tape and in the bioplastic, there was some growth inhibition.
So while we saw that there was some growth, not as good as the control group, we had to confirm whether the tape or the plastic was able to pass our biocompatibility. What we decided to do is do something called the Dunnett's p-test, which is a test that we can use to compare to a control group for um, multiple things that we're testing for. And with the bioplastic, we got a p-score of 0.18, which we can say passes. And with the tape, we got a score of 0.004, which we can say failed. So we did end up using the tape, but we ensured that the tape does not come into contact with the water. We believe that perhaps the adhesive has some chemicals in it that may stunt the growth of the algae. While the bioplastic was fine to use, we ultimately decided not to use it in our design for more design reasons.
This is a web server which for remote monitoring has temperature and OD reading and its graph shown every 16 seconds of the experiment, and it displays the status of the two motors and the fan. And for the remote control, we have a device that can stop the experiment or run it, which allows us to remotely intervene the experiment if we see there's an issue with the experiment.
To regulate both temperature and OD in our system, we implemented PID controllers. We use PID controllers to adjust the voltage of the components through PWM, controlling their performance. And the effective cooling system for the muscle tank in our setup is the pump controlled by the PID temperature controller. The PID constants were experimentally tuned using a test run that lasted 1 to 2 hours. We planned to run it overnight, but due to some errors, we ended up running the experiment only for 1 2 hours. Varied the proportional constant Kp across the wide range 0.001 to 1000, keeping Ki and Kd 0. The optimal Kp was selected based on the system response, with the best Kp fixed. Kd was varied over the same range to observe its effect. Finally, Ki was tuned using the same approach. To ensure valid results, we intentionally set system control variables away from the optimal conditions, allowing the PID control's performance to be properly evaluated under different dynamic conditions. The dashboard we built allows real-time monitoring of the system. If the temperature is high, the pump will be turned on to cool it down. If it's low, then the pump will be stopped and the system will let it heat up naturally, as shown in the video. To ensure accurate control, we characterized the pump by generating a duty cycle versus flow rate graph. This calibration was essential for translating PID output in terms of duty cycle into predictable fluid flow behavior. We validated the PID controller performance by analyzing the temperature versus time graph collected during the test run.
For the OD sensor, we chose this photodiode as you can see here, as we believe measuring direct light will get high accurate analog reading, ideal for OD computation. We then created a setup of two glass tubes in the diagram in the left, covered with aluminum foil for better light reflection and taped together with one end having the sensor here and the other end having the LED. We used the formula above to get the raw OD reading. Then by sending a known algae concentration across the tube, we took 3 measurements of the OD and plotted it against each other to get this formula, along with the error bars. And then we used this formula to find the algae concentration in the mussel bucket. We also used the flow rate of the motors and the algae feeding rate to get a proper estimate of the algae in the mussel bucket. Then we used the OD reading and the algae concentration calculation and this PID OD code to control the algae concentration in the mussel bucket. We found the PID constants using a PID tuning experiment, which we ran for a while for a different PID constant. And once we got the optimal PID constant, we used this code to control the algae concentration.
Store the values locally when we're not connected to a Wi-Fi network. What we just do is when the file is running, if it senses that it is disconnected from the Wi-Fi, it will start automatically storing locally, as seen and printed in the terminal here. Then, once we stop, like towards the end, when we're done with the experiment, we'll create the log txt file, and here we can see the different times and the temperature sensor reading and the OD sensor reading, and yeah. Okay, so to export the data and export the experiment parameters, we can just go into the Adafruit interface, and then as seen here, go download export the data as a CSV file. And then once we open the CSV file, we can see like the different parameters that it has stored.